Alrighty, section 8.5, multiplying and dividing rational expressions. So, again, multiplying is very similar to how we treat polynomials. Okay, so it's very similar to addition and subtraction in that it draws a lot of parallels. Recall that if you have two binomials, right, 5x plus 3, 6x plus 1, when you multiply them, you just have to make sure you pair up every single pair, right? And there's multiple ways to organize that. Feel free to use whatever organization you like. I just like to use distribution property. Take the first one, monomial times monomial, take the second one, monomial times monomial, right? That's all you need to do. You want to use a box to organize it, you want to use FOIL to remember, make sure you got everything, go for it. But that's what it is at the end of the day, okay? You're just multiplying each one. Same thing goes for when you're multiplying radicals, okay? So if you have these partial radicals, you have this root 5 plus 3, root 6 plus 1. It's the same thing. You can consider these binomials, right? And then you just multiply. Oops, I'm in eraser mode. Multiply each one. So the root 5 times root 6 becomes the root 5 times root 6. There's the root 5 times 1, root 5 times 1, right? That was the first one. Paired him up with everybody. Second one, 3 times root 6. And then the last one, 3 times 1. Okay? So again, if you have 4 terms, you just need to make sure all 4 combinations happen. From there, multiplying two radicals is just the product rule, as long as they have the same index. Otherwise, you can't multiply them together. You just have to leave them as they are. Multiplying by a number rarely turns out anything super different. And then multiplying a number by a number just becomes a number. So here we end up with 4 terms. Maybe in a binomial, you probably end up with some like terms that you can combine. Depending on your radicals, that could happen. But remember, radicals they're a lot pickier. They have to have the same index in order to be combined, right? In order to be combined, they have to have the same index to be added, and they have the same radicand. So they have to be the same exactly. So we can't combine 30, can't combine 5, and we can't combine 6, because those are all different radicands. Those are all different numbers under the radical. And obviously we couldn't combine it with 3. It's not even a radical. So let's try this out with some different radical things. Let's try with this first one. So I'll start with the first ones, right? So I'm going to multiply 7 to everyone. 7 to everyone. So 7 root 5, right? And then 7 root 2. Now I can do the last ones. Now I got to watch out. That's a negative. So negative root 3. Oops, I don't want to use green. I already used green, silly Miss K. Let's do red. So negative root 3 times root 5. And then the last one, negative root 3 times positive root 2. Negative root 3, root 2. Okay, I got 4 different terms, 4 different combinations. Easy peasy. And now we simplify. 7 root 5 is just going to stay 7 root 5. Same goes for 7 root 2. Let's just use our same color scheme. Just this first time, I'm going to use the same color scheme. So 7 root 5, and then 7 root 2. I don't need to simplify either one of those because those are both prime, right? They're both prime. No factors other than one in itself. Over here, I have negative root 3, root 5. Same indices, so I can combine them to a negative root 15. Same concept in the pink. Negative root 6. And since 15, 6, 2, and 5, none of those are the same number, that is my final product. Okay, easy peasy. Let's do another one. Root 10 times root 10. I get root 10 times root 10. Root 10 times negative root 3 would be a minus root 10, root 3. Oops. Root 3 times 10 would be a plus root 3, root 10. And then root 3 times negative root 3 would be negative root 3, root 3. Now I can combine using product rule. So I'll combine all these using, oops, I wanted to press product rule. Square root of a 10 times square root of 10 is the square root of 100. That's the same thing as just a positive 10, right? Positive 10. Actually, I'm going to write that a little small. Square root of 100 That reduces to a positive 10 if we take the principal root. Now we've got square root of 10, square root of 3, both square roots, so square root of 30. Square root of 30 over here as well. And then the last one, we have square root of 3. Oops, should have chosen pink. Sorry. That's going to be the square root of 9, which reduces down to 3, negative 3. And then if we check the middle here, we have two like terms. Square root of 30, square root of 30. 1, so I'd add their coefficients. Negative 1 plus 1, they end up canceling each other out. I'm just left with 10 minus 3, or 7 as my final answer. So sometimes when you multiply a whole bunch of radicals, the radicals go away. That's a coincidence. It just happens. Well, it's not really a coincidence. It's because these are what we call conjugates. We're going to talk about that in a second. It's a very powerful thing when you're rationalizing. But know that sometimes it happens. Think of them kind of as difference of squares, right? Or think of them kind of as, difference of squares. So that when they do, they end up canceling out. You end up just getting a 7. Okay? It happens. Regardless of whether you see it or not, it will happen. Okay? Let's talk about this one. This one's super important as well. Root 7 minus 3 squared. Remember, I am not going to do that. Absolutely not. Do not distribute because there's a minus sign there. I can't. Instead, think of this as a root 7 minus 3 times a root 7 minus 3. Multiply each individual one now. Those guys, root 7 times root 7. And then those ones, minus 3 root 7. Minus 3 root 7. And negative 3 times negative 3 would be a positive 9. We'll write it the same way. Negative 3 times negative 3. Right? This first guy is going to simplify to a root 49, or better yet, a positive 7. Careful, these do not cancel each other out, right? They do not cancel each other out. They do not cancel each other out. So I here get negative 6 root 7. Oops. Negative 6 root 7. And then the last one, negative 3 times negative 3 would be positive 9. I can reduce this just a little bit by combining these like terms. 7 plus 9 is 16, minus 6 root 7. So if I distributed the 2 in, then I would just get 7 plus 9, which would be 16. I'm sorry, 7 minus 9, which would be, 7 plus 9, which would be 16. And I'd forget this 6 root 7 part, and that would be horribly off, especially if I was trying to send like a rocket into space and it was off by 6 root 7. Yeah, that thing ain't going into space. I tell you what, that thing's coming crashing back to the earth. So don't ever distribute stuff like that, okay? Let's do another one. Ooh, this one also looks like a difference of squares, the same kind of thing. We got some higher powers going on here. But again, higher powers, they're not special. It's the exact same thing. So I just multiply these two guys. 5 times 5. And then we have those two guys at the end, so there's the second combination. Plus 5 cubed root of 3. Those two guys, minus 5 cubed root of 3. The last one, negative cubed root of 3 times the positive cubed root of 3. Simplify. 25. Looks like these two guys are going to cancel each other out. And the cubed root of 3 times the cubed root of 3 is going to be cubed root of 3 squared, or cubed root of 9. Careful. I notice these two are not the same. I don't end up with just a 3 here, okay? Cubed root of 3 is not the same thing as the square root of 3. So that nth thing, that nth power rule, does not work. So I end up getting the cubed root of 9 as my answer. So yes, it was a difference of squares in a sense, quote unquote, but it didn't end up giving me a whole number. Excuse me. Okay, let's keep going. Try another one. This one is all squares, so hopefully the difference of squares will actually apply. But let's try it out just in case. So those two multiply, you get square root of k, square root of k. And now we'll do those two. Square root of k. I don't know why I wrote it. Positive, positive, square root of k, square root of y. Here we go. Negative, square root of y, square root of k. And then the last one, negative square root of y, square root of y. Okay. Alright, here we get square root of k squared, otherwise known as k. Here, these may not look identical, but when you stick them under the radical, right, you stick them together, you get plus root ky minus, and if we write them in alphabetical order, ky, and they do cancel each other out. Last one, you get square root of y squared, otherwise known as minus y. So we end up getting k minus y as our final answer. And it did work out as a difference of squares. Cool. So if it is actually squares, it ends up working out. It actually doesn't work out for fourths either. You end up getting like squareds and all stuff over the place. But most of the time, for squareds, for square roots, it'll work. For cubed roots, it will not. Let's try one more. So I've got 2 root 3 times 2 root 3 times 3 root 3. That would be 6. Oh, let's just write it up. 2 root 3 times 3 root 3. And then you get this one plus, no, it would be a minus because that one's negative. 2 root 3, 2 root 5. And then you have these two plus 5, whoops, plus root 5, 3 root 3, plus minus root 5, 2 root 5, sorry about that. Okay, now we can simplify. So I can combine the numbers. I get a 6. Root 3 times root 3 is the square root of 3 squared. So that would be times a 3. End up getting 18. Here I've got 2 times 2, so minus 4. Root 3 times root 5, root 15. So minus 4 root 15. Over here I've got root 5 times root 3 and just a 3, nothing in front there. So root 15. I changed my mind about writing that there. Come back to that in a sec. And the last one, root 5 times 2 root 5 is going to be 2, and then root 5 times root 5 is just going to be a 5, so we get a 10. We have a few like terms in the middle that ends up being a negative root 15. 10 and 18 and 10, oops, it's a positive 10. We can combine those, so we get 28 minus root 15. And that's the problem. 28 minus root 15. Coolio. Alrighty. So that's multiplying radical binomials. Okay, so multiplying radical binomials, not super different from multiplying regular polynomials, right? Multiplying regular binomials. So you just have to watch out for those product rules and what you can actually combine and not combine. Let's talk about something called rationalizing now. Excuse me. Rationalizing is when you have a polynomial, or sorry, a radical expression that looks like this. So you have a rational expression that looks like this, right? And the radical part, sorry, a radical expression that looks like this. It's a radical rational, essentially. It's a radical rational. The radical part is in the denominator. That is a problem. It is only a problem because it is ugly. Here's what we would do to fix it. What we're going to do is multiply by 1. We're going to multiply by 1. But we're going to multiply 1 as the denominator over itself. Okay? So we're going to multiply by those. When that happens, we end up getting a whole number on the bottom. Okay? So I'll show you with another one as well. Square root of 3. If I multiply that by 1, in other words, 3 over 3, root 3 over 3, then I multiply the tops, that just becomes root 3, right? And that's okay. But if I multiply the bottoms, I get the square root of 3 times 3 from the product rule, right? Or root 3 over the square root of 9. And we all know that square root of 9 is a positive 3. So now the denominator is a whole number. It is no longer a radical. That's what we call rationalizing. Okay, so that is rationalizing. Let's try that out with a few more. 3 over root 7. I want to multiply by 1, and I want it to look like, let's do this down here. So 3 root 7. I want it to look like the denominator over itself, because I'm not actually changing anything when I multiply by 1. So I can multiply by the denominator over itself without changing the number. I end up with 3 root 7 on the top. Root 7 times root 7 is the same thing as root 7 squared, or root square root of 49, or 7. Notice it takes that number and it makes the radicand a whole number, so it gets rid of the radical in a sense. We end up with 3 root 7 over 7. The next one, 5 root 2 over root 2. Do we need to rationalize here? We actually don't, because I can consider this as 5 times root 2 over root 2, right? In other words, 5 times root 2 over root 2, or just 5. I don't need to rationalize here because it's already able to be canceled out. That's another way to rationalize. If your number can be reduced, you don't need to rationalize. It's only when things can't be reduced that it becomes a problem. Okay, so make sure you can always reduce first. Here I have negative 6 over root 12. So let's rationalize by multiplying by root 12 over root 12. End up getting 6 root 12 over, negative 6 root 12 over 12. Let's see if we can simplify that 12 a little bit. Well, we get 3 and 3, so 3 and 4. I'm sorry, simplify this 12 a little bit. So that's 6 times 2 times 2 times 3 over 12. Go down here. Negative 6 times 2 root 3 over 12. Negative 12 root 3 over 12. Hey, look, those cancel. I end up with negative root 3. So always remember to include those other simplification rules as well. Let's do one more. Let's do a couple more. Negative root 18 over 125. Again, this one, let's try it. So first let's apply quotient rule. Let's keep all those other things in mind, all those other tools we have in mind. So this would be negative root 18 over root 125. Do I need to rationalize? No, because root 125 is, no it's not, that's a cube root, just kidding. I do need to rationalize. Yep, the square root of 125 is not 5. I was mistaken, that's the cube root, right? So we need to rationalize this. We'll start by multiplying by, let's multiply by root 125 over root 125. That becomes, let's see, negative root 18 times 125 over root 125 squared. 18 times 125 is 2250. That's equal to negative square root of 2250 over 125. Let's see if we can divide that by 5, 10. Okay, so 225, I'm going to reduce that part down. 2250, sorry. 2250 breaks into 90 and 25. That breaks into 10 and 9. Breaks into 5 and 5. That's going to be 3 and 3. And that's going to be 2 and 5. So it looks like 15 root 10 equals negative 15 root 10. Over 125. And if I divide those both by 5, I get negative 3 root 10 over 25 as my final answer. So I started by rationalizing, right? I rationalized the 125 over 125. I got that. I reduced that one down to get negative 15 root 10. And then I simplified the 15 and the 125 down into 325. There we are. Okay. Let's try another one. This time with some variables. Could be fun. So I have here a quotient under a radical. I think I'm going to change it to 2 radicals and a quotient. So I have root 50 m to the 4th over root p to the 5th. Let's simplify first. I'm actually going to write it up here. So this would be root 50 m to the 4th over root p to the 5th. That's going to equal, let's see, 50 breaks into 10 and 5. 10 is 2 and 5, so 5 root 2. So 5, and then I've got m squared root 2 over p squared root p. So I started with that. Now remember, when I rationalize, the point is to get rid of the radical, not to get rid of the whole denominator. So by simplifying first, what I've done is made my rationalizing a little bit easier. I've simplified that so I can make my rationalizing a little easier. Now I only need to multiply by root p, not root p to the 5th, right? So now I can do that on the top. I get 5m squared root 2p over root p times root p is going to be another p cubed. And nothing cancels because one p is under the radical, one's not. So that's my final answer. So try rationalizing first. See if that'll help you out. Last one. Let's try one of those higher powers again. Change that into cubed root of 27 over the cubed root of 16. The cubed root of 27 is 3. And I do believe the cubed root of 16 is not a whole number. Correct, it's 2.51. If it was a third, or if it was a fourth or a second, it would work, but it's just the cubed root of 16. Well, let's simplify it first. Let's simplify it. So if we simplify that over here, the cubed root of 16, that's going to be 4 and 4, or 2, 2, 2, and 2. So it's going to be 2 root 2, 2 cubed root 2. And then I just have to rationalize by the cubed root of 2. Right? I only have to rationalize by the radical part. That's all I care about. So I end up getting 3 cubed root of 2 on the top. I have a 2, and I'm going to get another, whoops. Sorry. Let's talk about this. Rationalizing with the cubed. Head back up. My bad. I was so eager to get this done. When I rationalize by that, remember that, so if I were to rationalize by just this, that's not going to end up going away, right? I'm going to end up getting 2 squared under the cubed root, and that's not going to help me. I need to multiply by 2 of them. If I multiply by 2 of them, then I get a group of 3, and the group of 3 cancels out. You see how that worked? So now I have up at the top 3 cubed root of 4 over. Here I've got that 2 still, but I've got the cubed root of 2 times 2 squared, or the cubed root of, 2 times the cubed root of 2 cubed, and now it cancels out. So what I want here, my final answer, over here, 3 cubed root of 4 over 2 times 2 would be 4. So basically multiply however many you need, right? Up until now, we've been dealing with squares, and I think I skipped, oh no I didn't. We've been dealing with squares, and so the squares only require 1 additional one. If you have a cube, you're going to need 2 additional ones to make a group. If you have a fourth, you're going to need 3 additional ones to make a group. The whole point is you want to make a group and get rid of the radical, right? You want that nth power thing to cancel out. So I had to multiply by 2 of them here. And that's it. Okay, so that's rationalizing when you have a monomial. However, we've seen things that don't have monomials in the denominator. We've seen lots of things that don't have monomials in the denominator. You can still rationalize a denominator that has a binomial. So we're going to do monomials and binomials. We won't get to trinomials quite in this chapter, maybe even this year, but we will do binomials, okay? Let's talk about something called the conjugate. The conjugate we've actually seen a few times today. The conjugate is specifically for a binomial. A conjugate takes the two terms, they're exactly the same, but they have opposite signs, okay? They have opposite signs. That's what a conjugate is. So, for example, 2 plus root 3, its conjugate would be 2 minus root 3, okay? And you may be thinking, okay, so why do I care? The conjugate, when you multiply it, ends up giving you a whole number in a binomial. And I will prove it to you. Let's go back to some of our multiplication earlier. Here we had a conjugate. Root 3 plus, or root 10 plus root 3, root 10 minus root 3. We ended up getting 7, right? Root k minus root y times root k plus root y. We ended up getting k minus y. You don't see any more radicals, right? No more radicals there. It doesn't quite work for cubics. Sorry. Only works for squares in this case. And I may be forced. I haven't really thought about it yet. So we will only be doing with cubics. But, with conjugates of squares. Right? That's the only place that we're going to have it help out with the multiplication. But that's basically what it is. You take the first one, the terms themselves are the same, the operation is the opposite one. Okay, so let's see if we can find some conjugates for some different things before we go multiplying it all. What would be the conjugate for 3x plus 4? It's a binomial. I would keep the terms the same, but I would change the operation. That would be the conjugate for 3x plus 4. Same thing over here. Keep the terms the same, 9y and 3z, but this time it'll be a plus. That would be the conjugate. Okay, cool. Root 3 plus 12 becomes root 3 minus 12. The cubed root of 187 stays the cubed root of 187. And the fourth root of 96, except you change the sign. Okay, so conjugates are pretty easy. They're easy to find. You just have to switch the sign. And like I said, the only thing we're going to be worried about is binomials. So you don't have to worry if there's a trinomial and which sign do you switch. It's just going to be a binomial. Okay, cool. Here's an example of what I was just talking about with when they multiply, they go away. Basically, the main idea is this happens. You end up with two terms in the middle that cancel and one on the end that becomes a whole number. Okay, so that's the whole point of a conjugate. Conjugate's very, very similar to difference of squares. Okay, so difference of squares, if you were to multiply that, you end up with 9x squared minus 16, right? You get rid of those middle terms. Same thing happens with radicals. You get rid of those middle terms, and the last one also gets rid of the radical as well. That's why it's so important. So we're going to use conjugates to rationalize denominators, just like we were doing before. But this time we can't multiply by itself, because that's not going to cancel out. We're still going to have radicals. This time we're going to multiply by the conjugate. So I have here my first example, 5 over 4 minus root 3. The conjugate of 4 minus root 3 would be 4 plus root 3, right? What I do to the bottom, I have to do the top. So I found the conjugate. Now let's multiply. Well, the numerator is just going to be 5 times each of these. So 20 plus 5 root 3 over, and let's do the conjugate multiplication down here. So I have 4 minus root 3 times 4 plus root 3. 4 times 4 is 16. 4 times root 3 is positive 4 root 3. Negative root 3 times 4 is negative 4 root 3. And then root 3 times root 3 is going to be a negative. And then root 3 times root 3 is root 9, or 3, right? Those two end up canceling out. I get 6 minus 3, or 3. So this bottom up here would be 3. And that's my final answer. So notice we have now rationalized this because there's no longer a radical term in the denominator. There was two terms in the denominator to begin with, but one of them was a radical, so we got rid of it. Let's do the same thing over here. Alright, what would be my conjugate here? I have root 5 plus root 3. The conjugate would be root 5 minus root 3. And I'll multiply the same thing I do to the top as I do to the bottom. I'll do the first one in pink over here. I'll do the numerator over here. Root 2 minus root 3 times root 5 minus root 3. So root 2 minus root 3 times root 5 minus root 3. Just go term by term. Term by term. That would be root 10. That would be minus root 6. That would be minus root 15. That last one, root 3 times root 3 is going to be a positive 3. And I can't combine any of those because they are not the same radicand. So 10 minus root 6 minus root 15 plus 3. Okay. Let's do the second one. Hopefully the second one ends up being a radical, right? Or it ends up getting rid of the radicals. It should. That was kind of the whole point. Root 5 plus root 3 times root 5 minus root 3. A lot more in common here than the last one. Root 5 times root 5, root 25, or 5, right? Root 5 times negative root 3 is going to be negative root 15. Root 3 times root 5 is going to be positive root 15. And root 3 times negative root 3 is going to be negative 3. Those two cancel. I'm left with 5 minus 3, or 2. Ah, good. It did end up being 2. 10 is prime, 6 is prime, 13 is prime. I'm not prime, I'm sorry. It cannot be reduced, so I am done. That is my final answer. So for the next one, we have square root of 5m minus square root of p over, that's the denominator under 3. So let's multiply by the conjugate. The terms stay the same, just this time it's plus. Alrighty, we'll do the bottom one first. Root 5m minus root p, root 5m plus root p. 5m times root 5m times root 5m is going to give us 5m squared, square rooted, so just 5m, plus root 5mp minus root 5mp plus p, right? So, sorry, minus p. So those cancel out. We end up with, as a denominator, 5m minus p. For the numerator, we'll just multiply to 3 to everything. So we get 3 root 5m plus 3 root p. That is in simplest form, so there we go. Last one with conjugates. Alright, the conjugate of this guy would be, again, the opposite. So root x plus 2 root y, and therefore the same thing on the top. Multiply the bottom. By now, hopefully you can see the pattern that you end up getting the subtraction of the two. So x minus 2y, whoops, I don't know why I put it there, equals x, not cool, dude, x minus 2y. Over at the top, we get 3x times 3 root x times root x. That's going to be 3x, right? The roots cancel out. 3x times root y, so we're going to get plus 6 root x y. And there's our final answer. Alright, so hopefully conjugates are pretty straightforward, and multiplying them just goes straight off of what we were doing in the beginning of this video, multiplying two things together. The very last thing we're going to talk about is, simplifying these radical expressions that have monomials in the bottom. So writing radicals in lowest terms, essentially. When you look at it this way, you have to remember, you can't just start canceling, right? You can't cancel all over the place. What you can do, though, is if you split it into two fractions, or even better, split it into two fractions and make the fraction of the second one a coefficient rather than part of it, then you can start reducing. Notice here, 6 over 4 reduces to 3 halves, right? And here, 2 over 4 reduces to 1 half. And then from here, we can see we still have the same base. So if you wanted to leave it this way, that's one option. You could also put those together again over the same base. Sorry, that was kind of ugly looking. Let me write it again. The same base. So that would be our pretty much reduced final form. 3 plus root 5 over 2. Really the main point, you can keep them as one fraction as you go through and do this, but you got to make sure you cancel both things, right? So you cannot cancel just a 6 and a 4. You can't cancel, or reduce, I should say, just the 2 and the 4. You have to make sure you do both parts. That way you get down and you reduce both of them. Let's do one more real fast. I can split this up into 5y over 6y minus root 8y squared over 6y. Very easy to reduce the first one. These y's cancel. I end up with 5/6, right? In the second one, let me start by reducing that square root part. So square root of 8, again, not 2, right? That's the cubed root 8. But we know that we can reduce that to 2 root, a 2, and then what's left is root 2, right? So I have a 4 that I can bring out. Y squared does reduce to just y. That's over 6y. Those two y's are going to cancel, and actually the 2 and the 6 will reduce to 1 and 3. So I end up with 5/6 minus root 2 over 2. Root 2 over 3, pardon me, root 2 over 3. You can do it like that. Now, if you didn't want to do, if you didn't want two separate fractions, then you would just put them back together as 5 minus 2y root 2, 2 root 2 over 6. Okay, so that's one option to the other option. I just wouldn't reduce this part here. I would keep it as it is. Because I didn't want to reduce with the 5. This is not 5 root 3, so I can't reduce it down to 5 root 3. Alright. Hopefully that answered your questions about multiplication and rationalizing, otherwise known as dividing, and some simplifying within radical terms. If not, then shoot me an email. Otherwise, we'll see you in the next video.